Hello everyone, my name is Ziyang Liu. Let me introduce our work. Mutual a priori based completion for low overlapping point clouds registration. First, let us review the previous methods of point cloud registration. The first method is based on detection. This method cannot achieve reliable registration if the overlapping area is small and the information is insufficient, as shown in Figure A. The second method is based on completion. Multiple feasible completion results may lead to ambiguous registration results, as shown in Figure B. Our work continues with the second method, using completion to improve registration accuracy. Classic point cloud completion methods attempt to leverage prior knowledge from the training dataset and use objects from the dataset as references for completing partial point clouds, as shown in Figure A. A significant limitation of this approach is that the completion results tend to be biased towards the training objects and cannot be directly applied to unseen objects. Unlike classical methods, our proposed mutual prior method uses the partial point clouds to be registered as mutual priors to extend each individual point cloud, as shown in Figure B. In this case, the completion training set is primarily intended to provide continuous priors for the objects, and the completion model is no longer biased towards the object categories in the training set. We compared our method with recently published methods, including CTFNet, RPMNet, Finet, Predator, REGTR, GeoTransformer, and UDPREG. The results indicate that our method demonstrates highly competitive performance. As shown in the figure, we conducted comparative experiments on Modellinet, and our method exhibits good performance when facing low overlap point clouds, particularly showing a significant improvement in the translation accuracy of the registration results. Among them, CTFNet is a traditional completion-assisted registration method, while the others are based on point feature pairs. We also conducted experiments on the dataset proposed by CTFNet, where separate training is performed for different categories before registration. Our method follows this approach and achieves good registration results. The proposed MPC method is particularly effective for point cloud pairs with lower overlap areas, and its performance can significantly outperform the state-of-the-art methods when the partial value is 0.4. Compared to REGTR, the proposed method reduces rotational and translational errors by 30.8% and 57.7%, respectively. Furthermore, MPC achieves competitive performance on Modelnet and Modellinet, achieving the best results in 5 out of 6 test cases. On the challenging CTF dataset, the proposed MPC method also achieves very competitive performance. Specifically, compared to traditional completion-assisted registration methods, it reduces the previous best rotational error by 20.1% and the previous best translational error by 31.5%. The pipeline of the MPC, 3 key modules, spatial mutual prior SMP, feature mutual prior FMP, and reconstruction mutual prior RMP, have been developed to align the partial point clouds to obtain high mutual information gain. Blue and red flow represent the completion tasks of P subscript X and P subscript Y respectively. Assuming that the completion of P sub X is the main task, and SMPs to generate a coarse rotation matrix are sub-0 to align the orientation of P sub Y to P sub X. Specifically, the SMP contains 2 encoders to extract the features of P subscript X and P subscript Y as L subscript X superscript S. Then, these features are fused according to that formula. The fused feature L subscript S is fed into a multi-layer perception to generate a coarse rotation matrix R subscript 0. The ground truth rotation matrix of registration task is used as the supervision information for R subscript 0. Through matrix multiplication, R subscript 0 can rotate the point cloud P subscript Y to an orientation P subscript Y prime similar to P subscript X, thereby providing better initialization for subsequent completion and registration operations. The initial rotation alignment matrix R subscript 0 from SMP module can only give coarse spatial alignment between clouds, which cannot provide reliable mutual reference for the subsequent completion task. Therefore, feature mutual prior FMP module is designed to make the feature space alignment between the partial point clouds to further improve their mutual information. The structure of the FMP module is shown in the figure. The FMP module takes the partial point could p subscript x and the rotated reference point could p subscript y prime as inputs, and uses feature extractors to obtain their representation L subscript x superscript f and L subscript y superscript f in the latent feature space. U subscript x serves as the final feature to generate the completion result C subscript x using the snowflake decoder, which encodes the information form both its main task feature and reference feature. In order to maximize the mutual information, a simple approach is to use p subscript y as the target of the completion results C subscript x that generated from p subscript x. The benefits of this mutual reference are as follows. Firstly, by taking each other as the references, the targets of completion are visible for both partial point clouds, which can avoid the ambiguity introduced in predicting the invisible parts. Secondly, the completion process is decoupled from the object category, so the completion results are less dependent on the object categories in the training set, and therefore have better generalization. Thirdly, it is not necessary to have the complete point cloud of the object as ground truth, and training can be accomplished by just using partial point clouds with known relative positions. The registration ground truth between p subscript x and p subscript y is defined as a rigid transformation, which can translate the point cloud p subscript y to the frame of p subscript x. Therefore, given the reference point could p subscript y, the completion ground truth of p subscript x is defined as this formula. This formula is the union of two partial point clouds in the frame of p subscript x. In a similar way, the ground truth of p subscript y can be generated in its frame and defined as g subscript y. Reconstruction mutual prior RMP module has two optimization criteria. Firstly, completion loss. The completion results C subscript x and C subscript y should match their ground truth G subscript x and G subscript y as good as possible. Secondly, mutual reference loss. The completion results C subscript x and C subscript y should match each other as good as possible to avoid the inconsistency for the same object. Both criteria can help to improve the mutual information between the point clouds. As shown in the table, adding the cross-reference loss reduces the registration error. An intuitive explanation for this positive effect is that the cross-reference loss attempts to reduce the inconsistency between the two completions. In FMP module, how to use the reference feature L subscript y superscript f to enhance the completion task of L subscript x superscript f is critical for the completion performance. Specifically, 5 different methods are shown in this table. Based on the results, following observation can be obtained. Firstly, direct concatenation of L subscript y superscript f, such as U subscript x superscript 0, gives worse results, which means the main task feature and reference feature affect the completion in different ways and cannot be directly combined. Secondly, residue feature of L subscript y superscript f can effectively improve the completion performance. As shown in U subscript x superscript 1 tilde U subscript x superscript 4, this means the difference between two features can provide importance guidance for the completion process. Thirdly, the calculation of residual features is not symmetrical, and the order of subtraction affects performance, as shown in U subscript x superscript 1 and U subscript x superscript 2. In the following sections, the U subscript x superscript 2 is used for all the experiments and simplified as U subscript x. A question naturally arises: how much can the overlapping region be increased? The overlapping regions are defined according to their nearest neighbor Euclidean distance. A improvement of overlap rate on model net 40 for different partial values. B improvement of overlap rate on CTF for different categories. C completion results of 0 point for partial value. D completion results of 0.7 partial value. Based on these results, following observations can be obtained. Firstly, MPC module can effectively increase the overlap rate for all the partial values and categories, and generally more than 15.0% improvement can be obtained for all the cases. Secondly, more improvement can be obtained especially for the low overlapping point clouds, such as 0.4 and 0.5 partial value, and both the overlap rate and standard deviation have been improved. Thirdly, C shows that MPC module can complete the parts with very low or even zero overlap, and D shows MPC work for the objects with nonlinear or relatively complex structures. The proposed MPC method is based on a simple assumption. the partial point clouds to be registered belong to the same object. This a priori assumption is valid in most point cloud registration scenarios, but it has not been fully and effectively utilized. Given this prior knowledge, this work effectively combines registration and completion tasks, and use the partial point clouds kin as the completion reference for each other. In addition, based on the mutual information maximization, a progressive completion structure is developed to make the alignment between the reference point clouds in 3 steps: spatial space, feature space, and completion space alignment. This is the end of my presentation. Thanks for your listening. If you have any questions, please feel free to ask me.